Okay, Assalamualaikum and good morning everyone. Thank you for joining in another live session for Physics EP025. I am Madam Fatin and today I will bring to you chapter 4, Magnetism. Bismillahirrahmanirrahim. Okay, before we start, I'm hoping that maybe we could make this session quite interactive, okay? Where I'm gonna do all the talking and questionings, and all you have to do is to listen and participate by putting your answers in the chat box when it comes to lesson check questions, okay? So sometimes during the lesson, after we finish one subtopic, we are going to have a quick lesson check, okay? So the first person to give the right answer for any question, you can screenshot your answer, okay, and then you can come and see me to claim your prize, okay. So you guys want to know what the prizes are? Okay, you need to find out for yourself. Okay, hopefully everyone could give your best attention throughout the lesson. Okay, there are basically 7 subtopics for chapter 4. Okay, that's quite a lot, but don't worry because today we are going to cover only the first 3. 4.1 magnetic field, 4.2 magnetic field produced by current carrying conductor, 4.3 force on the moving charged particles in a uniform magnetic field. Okay, let's start off with 4.1 magnetic field. The learning outcomes is for you to be able to define magnetic field, identify magnetic field source, and then sketch magnetic field lines for the Earth, bar magnet, current carrying conductors.
Share. Dia tak perlu share. Okay. Application itu masuk.
Okay, so 4.1, the learning outcomes is to define magnetic field, identify magnetic field sources, sketch magnetic field lines for the Earth, bar magnet, current carrying conductors. Okay, so the definitions of magnetic field is a region around a magnet where a magnetic force can be experienced. Okay, it is quite the same with electric field, where we are talking about a region. When a charged body goes into the region, it will experience a force. Okay, in this case, it is magnetic force. Okay, magnetic field can either occur naturally or by being produced. Okay, let's take a look at some of the sources for magnetic field. The first one is the Earth magnetic field. Okay, the Earth behaves magnetically like a giant bar magnet located at the center of the Earth. Okay, next is bar magnet, and I'm pretty sure you have learned this a lot in school. Next is straight wire, circular coil, and solenoid. So the last 3 are categorized as current carrying conductors. There must be current flowing through the conductors, then only magnetic field can be produced. Okay, so on the left hand side are the examples for natural permanent magnets. On the right hand side are the examples of how magnetic field can be produced. Okay, magnetic field can be represented by using magnetic field lines. The directions of the lines starts from the North Pole going into the South Pole. Okay, as you can see in the animation. So the lines are leaving the North Pole going into the South Pole. Okay, the lines could be either straight lines or curves that do not cross each other. Okay, and to identify the directions of the magnetic field, it would be easier for straight line because if the line is going to the right, meaning that the magnetic field is to the right. But for curves, the tangent of the curve is the directions of the magnetic field. Okay, still talking about the magnetic field lines. Okay, if in the diagram is with a greater number of lines, and if the lines are closer to each other, So this is indicating that the strength of the magnetic field is stronger. Okay, more lines and they are closer to each other, meaning stronger magnetic field. Okay, next, when the lines are parallel and equally spaced, it represents uniform magnetic field. Okay. Okay, besides that, magnetic field can be represented by crosses or dotted circles. Okay, where the crosses indicating the magnetic field lines enter the page perpendicularly, or we can say into the page. For the dotted circles, magnetic field lines leave the page perpendicularly or out of the page. Okay. So to help you remember this, maybe you can imagine that when something coming out of a hole, most of the time you will see the head first. Okay, then you remember the dotted circles. But when something goes into a hole, you will see the back of the thing, right? Then you remember the crosses. Okay, but these symbols not necessarily for magnetic field. Okay, we can also use these symbols to represent current and magnetic force. Okay, so magnets basically have two poles, north and south. If you cut the magnet in half, you get two smaller magnets. And if you cut it more, you get more smaller magnets. Okay? Okay, and no matter how small they are, it will always has north and south pole on the magnet. Okay, it will never occurs as a monopole. Okay. When the same poles facing each other, they will experience repulsive force. Okay, and for opposite poles, they experience attractive force. Okay, so these concepts are very easy. Okay, so the next learning outcomes for the first subtopic is for you to be able to sketch the magnetic field lines for the Earth, for the bar magnet and the current carrying conductor. So all these are the sources for magnetic field. Let's take a look at the first one, the pattern of the Earth's magnetic field. Okay. If we look at in terms of geographical location, so the top part is the North Pole, Kutub Utara, and the bottom is the South Pole, Kutub Selatan. Okay, but one thing you should know is that in terms of magnetic pole of the Earth, the South magnetic pole is known as the geographic North Pole. The North magnetic pole is the geographic South Pole. Okay, so basically they are the opposites. Okay, and the Earth's magnetic pole is what makes the compass usable for navigation. Okay, next we go to bar magnet. So these are some of the patterns around bar magnets. The first one is a common bar magnet. Second is the horseshoe shaped magnets. Here you can see that the lines are leaving the North Pole and going into the South Pole. Okay, but what if we have two bar magnets experiencing attractive force? Okay, so this is the patterns of magnetic field around the two magnets. Okay, the lines are leaving the north, going to the south. Okay, for repulsive force, this is the pattern. So we can see the lines are repelling each other, and that will cause a neutral point where the resultant magnetic force is zero. Okay, so these are the patterns for bar magnets. Okay, for the case of a long straight wire carrying a current, the magnetic field wraps around the wire. Okay, so the directions of magnetic field, either it's going clockwise or anti-clockwise, can be determined using the right hand rule. Okay, where the thumb is the directions of the current and the other fingers showing the directions of the magnetic field. Okay, for example, in this diagram, the directions of the magnetic field is going anti-clockwise. Okay. Okay, next, the pattern of magnetic field lines at the center of circular coil. Okay, here we can see the current is flowing in one direction, okay, through the coil. But if we see from a top view, the directions of the current is different on two sides. So we can see here the current is coming out of the page, and on the right hand side the current is going into the page. Okay, so here we are going to use the same rule, right hand rule. Okay, and this is the pattern that we will get for the center of the circular coil. Okay, on the right hand side, so we have cross over here. So this is indicating that the current is going into the page. So you can use your hand. Your thumb should be pointing downwards, and the directions of the magnetic field is going clockwise. Okay. On the other side, here we can see a dot. So the dot is referring to the current coming out of the page. Okay. So using the right hand rule, your thumb should be pointing upwards, and the directions of magnetic field is going anti-clockwise. Okay. So this is the pattern. Okay, next is the pattern for solenoid. Okay, so here we can see the magnetic field is concentrated at the center of the long solenoid. Okay, still remember, the more number of lines, meaning the strength of the magnetic field is stronger, okay, at that region. Okay, the field outside is weaker because the lines are further apart and less number of lines. This is for solenoid. Okay, so for solenoid, we are going to use the right hand grip rule to determine the directions of the north pole. Okay, so it's a bit different from a previous slide. Okay, for the thumb is the north pole. So just now we said the thumb is the directions of the current. Okay, and the other fingers is directions of the current. So they are the opposites. Okay, so let's take a look at the diagram. Here we can see that the current is coming in from the left side. So it's going from up to down to the back, up, down to the back, up, down. So your fingers should be following the directions of the current, up, going down, up, going down. So this is the directions of the north pole. Okay. But what if the current flowing in a different direction? Okay, so the current is going to the back, down, going up, down, going up, down, going up. So you need to reposition your hands and fingers, okay, to follow the rules. So here we will get the north pole on the other side, right? Okay, so get ready for your first lesson check. For this subtopic, there are going to be 2 questions, and if I'm not mistaken, each question is about 15 seconds. Okay, so make sure if you are the first one to give the right answer, please screenshot your answer and you can come to claim your prize. Right, so 1, 2, 3. Okay, time's up. So the answer is C, from north to south. Okay, we have one more. 1, 2, 3. Okay, time's up. So for uniform magnetic field, the lines are equally spaced. Okay, so that's it for 4.1. We continue with 4.2. Okay, the learning outcomes for 4.2 is to sketch the resultant magnetic field diagram at a point and then determine the directions of B by using right hand rule. C, determine the magnitude of magnetic field for long straight wire at the center of circular coil, at the center of solenoid, and at the end of solenoid. Okay, when a current flows in a conductor, the magnetic field will be produced. Okay, and then the directions of the magnetic field, as you have seen in the previous slides, is by using the right hand grip rule. Okay, the thumb is the directions of the current, and other fingers are showing the directions of the magnetic field. Okay, when we talk about magnetic field, we are talking about a region. Okay, but if you want to talk about the strength of the region, it is called as magnetic field strength. Okay, the other names for magnetic field strength are magnetic field intensity and magnetic flux density. The symbol is capital letter B. Okay, we've seen for a long straight wire, the magnetic field wraps around the wire. So the strength of the magnetic field varies with the distance from the wire. Okay, for example, if we want to calculate the magnitude of the magnetic field strength at point P, we can use this formula. B equals to mu naught I over 2 pi r. Okay, where I is the current flowing through the conductor. Mu naught is the permeability of free space. This is a constant value. Okay, but what is permeability? It is the ability of free space to allow magnetic lines to conduct through it. Okay, so what matters is that use this formula in your calculation. Sorry, use this value, this constant in your calculation. Okay, and then r is the distance of a point from a straight conductor. So this is the distance. Okay, for the case of having two long wires that are placed parallel to each other and carrying the same current. So in this case, same magnitude of current. When the currents are in the same direction, so in this case, the current are flowing down. Okay, so here we are going to use the right hand rule to sketch the pattern around the two wires and also at point P. Okay, so for wire A, your current is going down, so your thumb should be pointing down and the directions of the magnetic field is going clockwise. Okay, the same goes for wire B. Your thumb is pointing downwards and then the magnetic field lines is going clockwise. Okay, so this is the pattern around the wires. But at point P, we can see that the directions of the magnetic field lines are the opposites. Okay, so here is going, maybe if the magnitude is the same, you will have a neutral point. Okay, and in order to calculate the resultant magnetic field strength at point P, you can use the formula that you have seen just now. Okay, because they are the opposite direction, we need to minus. Okay. Okay. But in the case of when the currents are in the opposite direction, okay, so A, the current is going down, so use the right hand rule. Your thumb is pointing down, so the directions of magnetic field is going clockwise. For wire B, the current is going up, so your thumb pointing upwards. The magnetic field is going anti-clockwise direction. Okay, so at point P, the flow of the magnetic field are the same. Okay, and we have more lines over here. So remember, more lines indicating a stronger magnetic field. Okay, to calculate the magnitude of the strength, the resultant, we use the formula and this time we need to add the number. Okay, right, then move on to circular coil. So this is the pattern at the center of circular coil. To calculate the magnitude at point O, we use this formula. P equals to mu naught Ni over 2R. Okay, where the mu naught is the permeability of free space, R is the radius of circular coil. So here we have capital letter R. Just now for straight wire, we only have small letter r referring to the distance from the wire. Okay. N is the number of coils, the number of loops, and I is the current. Okay, then we move on to solenoid. Okay, for solenoid, there are going to be two formula to calculate the resultant at the center of the solenoid or at the end. Okay. For the magnitude of B at the center is by using this formula over here, mu naught Ni over L, or we can simplify to become B equals to mu naught small letter n I, okay, where the small letter n is the number of turns per unit length. Okay, okay, this one is at the center. Okay, we look at the magnitude at the end of the solenoid. So the formula, you just need to add the half, okay, 1 over 2. Okay, simple. Okay, next, the second session for lesson check. There's going to be 3 questions. Okay, so get ready. 1, 2, 3. Okay, time's up. Okay, all except magnetic flux. Okay, magnetic flux you will learn in the next chapter. Okay, next question. 1, 2, 3. Okay, time's up. The answer is A. So when the current are in the same direction, so the pattern is for the answer is A. Okay, I think we have one more. 1, 2, 3. Okay, time's up. The answer is D. Okay, if you paid your attention during the lesson, you should be able to answer the lesson checks questions. Okay, so we move on to the last subtopic for today, 4.3. So the learning outcomes is to use the magnetic force, meaning to use the formula. B, determine the directions of magnetic force. Describe circular motion of a charge in a uniform magnetic field. And then use relationship, centripetal force equals to the magnetic force. Okay, consider that we have a uniform magnetic field. Okay, and if there is a stationary electric charge in the field, okay, meaning it is not moving, the charge will not experience a magnetic force. Okay, no motion, meaning no magnetic force. Okay, but if the charge is moving with a velocity in a magnetic field, then it will experience a magnetic force. Okay, so the condition is that the charge should be moving with a velocity, right? Okay, as for the magnitude of the magnetic force, it can be calculated by using this formula. F equals to QVB sine theta, where F is the magnetic force, B is the magnetic flux density or other names, V is the velocity of the charge, Q is the magnitude, and theta is the angle between vector V and vector B. Okay, in vector form, it is written as vector F equals to Q times vector V cross vector B. Okay, so from the formula, we know that it is a cross product. So for cross product, in order to get a maximum magnitude, the angle should be 90 degree. Okay, next, To determine the directions of magnetic force, there are two ways. The first one is using Fleming's hand rule. Okay, for positive charge, we will be using left hand rule, Fleming's left hand rule for positive charge, where the thumb is the directions of the force. B is the first finger and V is the second finger. Okay, this is for positive charge. For negative charge, we use the Fleming's right hand rule. Okay, so you can use the suitable hand for the suitable charge. Okay, another way is by using the right hand palm rule. Okay, so where the thumb is the directions of the velocity, the other fingers are the directions of the magnetic field, and your magnetic force is coming out of your palm. Okay, so let's compare with the Fleming's left hand rule for positive charge. Okay, so they are in the same position, always 90 degrees to each other. Okay, so you can choose either of these two that you think easier for you to answer questions. Okay, let's take a look at one example. Okay, determine the directions of magnetic force. Okay, you can either use the right hand palm rule or the Fleming's left hand rule, because here we have positive charge. Okay, let's say you are using the right hand palm rule. The V should be pointing, your thumb pointing to the right, your other fingers pointing down. So the directions of the magnetic force is coming out of your palm. Okay, so if you're using Fleming's left hand rule, so this is the position of your fingers. So the answer is into the page. Okay, right, then we go to the next one is to describe circular motion of the charge in a uniform magnetic field. Okay, consider we have a charged particle with a velocity moving perpendicularly into a magnetic field. So here we have dotted circles, meaning we have uniform magnetic field coming out of the page. Okay, and then there is a charged particles. Okay, the black arrow is the velocity, is going perpendicular into the field. Okay, what happens when a charged body with a velocity moving into a field? It will experience magnetic force. Okay, so here the black arrow is the velocity, the green arrow is the magnetic force. Okay, so you can see the directions of velocity changes, but the directions of F remain perpendicular to V. So they are always 90 degree. Okay, so the magnetic force makes the particle moves in circular path. Okay, so let's take a look at some example. Here we have a uniform magnetic field. So because we have dotted circles, meaning the field is coming out of the page. Okay, then we have a positive charge moving into the region. Okay, can you identify the directions of the magnetic force? So B coming out, V going to the right, so the directions of F is going down. Okay, so because there is a force acting on the charge will no longer move horizontally in straight line. Okay, it will be pulled to move in circular motion. Okay, so next we have uniform magnetic field going into the page, and then positive charge traveling perpendicularly into the page, into the field. So what is the directions of the magnetic force? So your fingers, if you are using the right hand palm rule, your fingers is going into the page, your V is going to the right, so your the directions of magnetic force is going up. Okay, so then the particle will move in circular motion. Okay, So here you can use the relationship of centripetal force equals to the magnetic force. Okay, you have learned about circular motion in first semester, and we can see that the charge is moving in circular motion. So we can use the equation FB equals to FC. Okay, and expand the equation by using the formula QBB sine theta equals to mv squared over r. And if you are required to find the radius of the circular motion, you can rearrange by and using this formula. Okay, where m is the mass of the charged particles, v is the magnitude of the velocity, r is the radius of the circular path, q is the magnitude of the charged particles. Okay. So we have come to the last session of lesson check. Okay, so there are 3 questions. Okay, 1, 2, 3. Okay, time's up. So the answer is C, downwards. Okay, so you can use the right hand palm rule. Your 4 fingers is pointing into the page. Your V is going to the right. So you can see that the directions of the F is going up. Okay, but remember, right hand palm rule is for positive charge. Now we are having negative charge. So the directions of magnetic force is the opposite. Okay. Right, lesson check 7. Okay, time's up. The answer is A, leftward. Okay, so your fingers pointing into the page, your V is going up, so your force is going to the left. Okay, and this is positive charge. Okay, the last one. Okay, time's up. So the true statement is A. Magnetic field exerts force only on a moving charge. Okay, this one is in 4.3. Okay, I think that's all for today. Thank you for your attention. Please scan the QR code for your attendance. Okay, and don't forget the winners. You can come to me and claim your prizes. All right, thank you.